Geometry notes, transformations, section 3. This gets into some pretty specific, gritty stuff. If you take the time to study these notes, you will be thankful. If you don't take the time to study these notes are pretty much pointless. End lecture. Reflection definition. A reflection is a line M, that's supposed to be lowercase and cursive. A reflection in a line M is an isometric transformation. Isometric means congruent, rigid motion. That maps every point P in the plane to P prime, so that the following properties are true. If P is not on line M, then line M is the perpendicular bisector of P, P prime. So here is line M. Here is point P, and it's not on line M. So this is saying if P is not on line M, which it's not, then line M is the perpendicular bisector of P, P prime. So if I draw a dashed line here, it's going to be perpendicular, and line M also cuts that in half, so that this and this are the same length, and this forms 90-degree angles. This is for reflectional symmetry, or reflectional transformation, I should say. If point P is on line M, then P equals P prime. Now, this contradicts something that I've been telling you all year long. And it's a symbolism that I don't care for, but it exists, so we have to use it. This just means same location. You cannot say that 2 points are equal. Makes no sense. In this context, me saying P equals P prime, I'm saying they're in the same location. So here's line M. Let's say P is here, and I reflect it over line M. Well, P prime is going to be in the exact same spot. It's the same point. Symbolically, how could we write this? We could say we're going to reflect point P over point M, and the result is P prime. Lowercase r is reflect. This is the line of reflection. This is what we're reflecting in the pre-image, and this is the image. A line of reflection is the, we've already stated it, perpendicular bisector of the segment joining every point in its image. So let's check this out. We're supposed to reflect about line M, triangle ABC, to get triangle A prime, B prime, C prime. So let's draw a random triangle ABC. Just to make my life easier, I'm going to make the line of reflection a vertical. Make this a little bit smaller. So how do I reflect it? The line of reflection is the perpendicular bisector of every segment joining the point in its image. So if I take point B and I draw a horizontal segment, because my line of symmetry is vertical, and I measure that distance, and I copy it over here so that it's still perpendicular, this should tell me exactly where B prime is. If I take A and I draw this, and I measure that distance, and I make it 90, and I copy that down, that should tell me exactly where A prime is. If I do the same thing with C, and I copy that down, exact same length, that should tell me exactly where C prime is. then if you connect the points, you've got your image and your pre-image. Pre-image is purple in this case, and the image is green in this case. Point being, every point in the pre-image and image is equidistant to the line of symmetry, and that distance is measured as the perpendicular distance. Characteristics. These are characteristics of reflections. Distances from the pre-image to the image. Points in the plane move same distance or different distances? Well, A moved this distance, B moved a shorter distance, C moved the largest distance. So these points are moving different distances, depending on their distance from the line of reflection. The further away you are, the further you're going to move. Points further away from the line of reflection move a larger distance. I just said that. Largerest? Idiot. Then those closer to the line of reflection. Notice how, well, this is important. A prime, that line, is parallel to B prime, which is parallel to C prime. These lines that we drew here to help us get those points, they will always be parallel to each other. Orientation. The pre-image has same orientation or reversed orientation. Well, let's discuss what orientation means. If I go around this pre-image, I would go around clockwise to get from A to B to C. But if I go around this other image from A prime, B prime to C prime, I'm going to be going counterclockwise. That tells us the orientation is reversed. When we say orientation, could you get to the same letters in the same order, either clockwise or counterclockwise? If the answer is no, it's reversed. If the answer is yes, then it's not reversed. This reflection creates a mirror image. Special points. Are there any special points in this? Yes, points on the line of reflection do not move. Special points are points on the line of reflection because they don't move. There is a ton of information that we just went over for reflectional symmetry or for reflectional transformations. Transformations and translations are different words. Transformations is all the different types of things you can do to move it, and a translation is a specific type. Translation. An isometric transformation that maps every 2 points A and B in the plane to A prime, B prime. So the following properties are true. A prime is equal to B prime. That means it's a fixed distance. A prime is parallel to B prime, a fixed direction. Let's see if I can give you some deets about this. I don't remember if we've talked about vectors yet. If we haven't, say hello to vectors. You can represent vectors in lots of ways. One way is to use one of these fellas at the beginning and end. This first number is telling us to go left or right. If it's negative, you go left. If it's positive, you go right. The second number here, which is where y is represented, that's going to tell you to either go up or down. Up is positive and down is negative. This is not an ordered pair, it's a vector. So for example, let's say that we had a pre-image that looked like this, and we were going to move that, let's say up and to the right, like so, giving us B prime and A prime. A prime and B prime are a fixed distance. So if I were to measure that distance, it would be the same as this distance. Also, it says that when you move it, you're moving it in a parallel way. For example, if this was a vector, maybe we went to the right 4 and up 1. Right 4 and up 1. Notation. Big T is a transformation. This is the vector. How many units left? How many units right? So this says translate triangle ABC by vector XY to get the result of triangle A prime, B prime, C prime. So let's give an example. Let's say that we want to translate by vector 5, 2. 5 to the right, 2 up. And we want to do that with triangle ABC so that we get triangle A prime, B prime, C prime. So let me take a triangle, ABC, and let's say we're going to move it to the right 5. 1, 2, 3, 4, 5, and we're going to move it up 2. 1, 2. Let's say it ends up being someplace like this. So these are our primes. Let me color code this for your viewing pleasure. Pre-image is green, image is blue. And let's say that we translated it in this manner, in this manner, in this manner. All these are going to be the same length, and they're all going to be parallel to each other. Cool. Characteristics. Points in the plane all map at the same distance or different distances. Translation is all the same distance. Orientation. Does the pre-image have the same orientation or a reversed orientation? Well, if I go around this clockwise, it's A, B, C. If I go around this clockwise, it's A prime, B prime, C prime. It's the same. Are there any special points? In the last one, we had some points that didn't move. If the point was on the line of symmetry. This has no special points. Everything moves the same. Special translation property, translating an angle along one of its rays. Now this is wacky stuff. A translation of angle ABC by vector BA maps all points so let's draw angle ABC. There's ABC. We're going to translate it by vector BA. Now, vector BA, now this is not to be confused with a ray. This looks just like a ray. How do we get away with being a vector? We write the word vector here. This is vector BA. What that means is we're going to move in the direction from B to A, and that is a length. This is the exact length that we are going to move. Grab this whole thing. Hold on a second. We're going to move this whole thing in this direction, that length. So B comes up here, A would be up here, and C would move up to here. So let me just draw that real quick. Copy, copy, copy. Each point gets moved by that much. So that means that B prime ends up being in the same location as A. A prime has moved to here, and C prime is moved to here. So what does this say? Translation of angle ABC by vector BA maps all points so that angle ABC is congruent to angle A prime, B prime, C prime. It's an isometry. Well, we knew that because translations do that. BA, B prime, and A prime are all collinear. See how they're all on the same line? So if I draw this new angle, it's going to be like so. And then the last thing that it says about this, I'll tell you what, I'm just going to put this up here. Not that it matters. Because the two angles are equal and formed on the same ray, then ray BC is parallel to ray B prime C prime. So this is going to be parallel to this. I'm not sure how important this special translation property is, but there it goes. All segments that are translated are parallel to each other. That's important. It's in red. We've talked about that already. Rotational definition. A rotation about a point O through theta degrees. This is a Greek letter, theta. Oftentimes in math, for angles, we use Greek letters. Is an isometric transformation that maps every point P in the plane to P prime so that the following properties are true. If point P is not point O, where O is the point of rotation, then OP equals OP prime, and the measure of angle pop prime equals theta. So let's talk about symbols. Rotation is a capital R, point of rotation, and then the amount of degrees of rotation. What are we rotating? Segment PX, and that's going to give us segment P prime X prime. Oh, in this case, let's say that we're rotating about point P, not point O. So here is PX. Actually, let's draw it this way. PX, some random segment. We're supposed to rotate about point P. So what that means is this thing is going to rotate like this. P's not moving because P's the point of rotation. We're supposed to rotate it theta degrees. Now theta is a variable, so we don't know how many degrees that actually is. P hasn't moved. P is in the same location that P prime is in. Let's reread this. If point P is not point O, that would be X in this case. So if X is not point O, then I should have used probably should have used these letters. Oh well, I didn't. So in other words, this distance and this distance is the same, and this angle is this angle of rotation. If point P is the point of rotation, which it is in this case, then P and P prime are in the same location. The center of rotation is the only point that is not affected by the rotation. So let's look at a bigger picture, pun intended, of a rotation so we can try to figure out what's going to be happening. A rotation is an isometric transformation that turns a figure about a fixed point called the center of rotation. So the notation is big R, center of rotation, and how many degrees you're going to move it. An object and its rotation are the same shape and size, but the figure may be turned in different directions. So for example, just going to trace over this. I'm going to try to trace over it. So what's happening here, this figure is being rotated around to get to here. You see that? Now, what you might notice, look at the distance that C is traveling. Focus on C. Let me make sure this is clear. This is C right here, denoted by the letter C. Notice C moves, doesn't move that far. Now let's focus on B. Does B move the same distance? Probably not, or wouldn't be asking, am I right? So B, as we rotate it, oh, it's moving farther. If you look at A, the top point, it's moving even farther. So I think it's safe to say, let's answer these questions. We'll get to this in a moment. Distances from the preimage to the image. Points in the plane, they move in the same distance or different distances? Moving different. Depending on their distance from the center of rotation. Points farther away from the center of rotation move a distance, it's supposed to be a line there. Move a larger distance than those closer to the center of rotation. Notice how segment A prime, and B prime, and C prime are not parallel. Let's look at the picture. If I draw A prime, B prime, and C prime, notice how those are not parallel to each other. I mean, it's obvious. That's not me just drawing it poorly. There's no way those are parallel. So that's important. Orientation. Preimage has the same orientation as the image. Special points. The center of rotation is the only point that is unchanged. Almost finished here. Before we get to equivalent rotations, it's important to note that if you rotate counterclockwise, that is a positive rotation. So let's say that we went from here to here. That's a positive 90 degrees. If we rotate the way that a clock goes, that is a negative rotation. Counterintuitive, but that's how it is. Equivalent rotations, coterminal angles. Now this is being glossed over, then you're going to be asked on your homework to find coterminal angles. Coterminal angle are, this says con, son of a motherless goat. It's supposed to be CO terminal, not con terminal, coterminal. How has that been wrong for this long? Ugh, it's embarrassing. Coterminal angles. You take the initial angle you're given and you add 360 degrees plus n, where n is the number of rotations that you have. So what does that mean? Let me give you a picture of coterminal angles. This is a really important concept in pre-calculus. Show you this in a coordinate plane. So we usually call the positive x-axis 0 degrees, which would make this 90, this 180, this 270, and I get back to here and it's 360. If I keep counting by 90s, I'm going to get 450 degrees, 540 degrees, 630 degrees, 720 degrees. I could just keep going on. If I draw an angle, this red angle, so that it stops right here, that's clearly 90 degrees. However, let's say that I wanted to have some fun with this and I wanted to go completely around and then stop here. Well, how many degrees is that? That's 360 plus 90, that's 450 degrees. 450 degrees and 90 degrees are considered coterminal because their terminal side, the side that moves, it stops in the same location. Since they stop in the same location, they are complete revolutions apart from each other. This represents a revolution, 360 degrees, and represents how many revolutions you're going to make. Could be 1, could be 2, could be 50, could be none. Coterminal angles, you take the initial angle plus 360 times however many times you want to go around. Please let me know if that doesn't make sense to you. Special rotation, rotation of 180. It's a special case. A rotation of 180 degrees maps A to A prime such that. So let's draw this. So here is our point of rotation. Here's point A. Just going to draw a segment, goes through that. like so. If you're rotating this, let's write this properly. Rotate about point O, 180 degrees, point A, we're going to get A prime. 180 degrees would be over to here. So it's going to put A prime over here. The following things are true. Measure of angle AOA prime is 180 degrees, obviously. OA and OA prime are equal. Ray OA and ray OA prime are opposite rays. Line OA, AO, is the same line as line A prime. There you go. That finishes the notes. There's a lot of stuff here. You would want to study these things. Figure out similarities and differences between these different types of transformations. Thank you very much.